The topic of this video is probably obviously disconfirmation. As you'll recall from previous videos, confirmation is positive support for a hypothesis providing us with a reason to accept the hypothesis. So, unsurprisingly, disconfirmation is support for the rejection of a hypothesis, and it provides us with a reason to reject the hypothesis. Let's go to our favorite example of this chapter, that of the geocentric system versus the heliocentric one. So before, we were looking to confirm the Copernican model. Now let's talk about an argument in which we try to disconfirm the Ptolemaic model. Okay, so here's a simple version of such a disconfirming argument. Premise 1. If the Ptolemaic geocentric model is correct, then Venus will not show a full set of phases, where the phases talk about like the phases of the moon, crescent, gibbous, all this sort of thing. The Ptolemaic system predicted slight variation in the size of the crescent showing of Venus, but not the full set of phases like the Copernican system predicted. Second premise, Venus does show a full set of phases, contrary to this claim up here. The conclusion, the Ptolemaic system is not correct. Note that in this argument, the first premise, if the Ptolemaic system is correct, then Venus will not show the full set of phases, is a conditional. And this is a term we've covered before. We defined a conditional as a sentence that expresses a relationship between two conditions, such that if the one condition is the case, then the other condition must be the case too. Here, the two conditions are the Ptolemaic system is correct, that's one condition, and Venus will not show the full set of phases is the other condition. The relationship between these two conditions, according to this conditional, are that if this first one's true, if it's the case that the Ptolemaic system is correct, then Venus will not show the full set of phases. Linguistically, conditionals can be expressed in a variety of fashions, and we'll look at some of those more in the next chapter. But you don't have to worry about that now. The simplest form of a conditional is this if-then construction, where the first condition, which is called the antecedent, follows the if, and the second condition, called the consequent, follows the then. So the sentence, if the Ptolemaic system is correct, then Venus will not show a full set of phases, is an example of this simple form, where the Ptolemaic system is correct, is the antecedent, and Venus will not show a full set of phases, is the consequent. Okay, let's take a look at the form of the argument. If we will let H stand for our hypothesis, and the hypothesis we're considering is that the Ptolemaic system is correct, and P for the prediction, and our prediction is that Venus will not show a full set of phases. Understood this way, the form of our argument is if H, then P. P is false, therefore H is false. Note that unlike the inductive argument for the Copernican system we saw earlier, this argument is deductive. Now, remember how we figure out whether or not an argument is inductive or deductive is to ask this question. If both of the premises are true, or all of the premises are true, depending on how many premises there are, is there any possible way in which the conclusion can be false? And if there's not, then the argument's deductive. Okay, so imagine a world in which it's the case that if H is true, then P is true. Meaning any time H is true, then P has got to be true. But then we learn that P is false. Well, if P is false, then H can't be true. Because any time H is true, then P is true. So we can conclude that H has got to be false. There's no possible way both these premises could be true, and the conclusion could be false. This isn't information that we had when we looked at the confirming argument. So that's why this argument is deductive, but the previous one wasn't. So if the premises are true, then the conclusion must also be true. Right. If this is true and if this is true, then this has got to be true. Of course, if one of these were not true, if we were mistaken in thinking that P is false, or we were mistaken in thinking that if H then P, well, then this conclusion might not be true. But it's still the case that this conclusion follows deductively from these premises. Thus, an apparent difference emerges between the confirmation of hypotheses, which we have said depends on complex inductive reasoning rather than a simple conditional argument, and the disconfirmation of a hypothesis, which can be deductively valid. So this discrepancy accounts for the greater enthusiasm that many scientists express for the method of disconfirming hypotheses over confirming them. This method looks particularly attractive when few hypotheses are available to account for the observed evidence. The reason why this is the case, because in such circumstances one might hope that the true hypothesis will emerge by elimination of false contenders. However, things are rarely this simple. For example, just like when trying to confirm a hypothesis, we also need to look at auxiliary hypotheses when attempting to disconfirm a hypothesis. Proponents of a view may try to save their view by rejecting one of the auxiliary hypotheses. In the case of Galileo, some proponents of the geocentric model try to discredit the auxiliary hypothesis that Galileo's telescope was reliable. So let's take a look at what that argument looks like with a couple of auxiliary hypotheses put in there. If the Ptolemaic system is correct, and if the telescope is a reliable instrument of observation, and if Venus lies between the Sun and the Earth, then Venus will not show a full set of phases. See, our conditional is more complicated now. The relationship isn't just between the Ptolemaic system and Venus not showing a full set of phases. It's between the Ptolemaic system being correct, the telescope being a reliable instrument of observation, and Venus lying between the Sun and the Earth. Our observation, and thus our second premise, remains the same. Venus does show a full set of phases. But now look at our conclusion. Rather than just saying that the Ptolemaic system is not correct, it's now disjunctive. It says either the Ptolemaic system is not correct, or the telescope is not a reliable instrument of observation, or Venus doesn't lie between the Sun and the Earth. What we now know is this full set of things can't be true given this observation. But which one do we get rid of? Let's take a look at what this looks like just in its form only. The form of this argument was if H and all the auxiliary hypotheses are the case, then P is the case. Second premise, but P is false. P isn't the case. Therefore, either H or one of the auxiliary hypotheses is false. The question in the case of the Ptolemaic system was which one. The answer turned out to be it was the hypothesis was false, and not any of the auxiliary hypotheses. But how do you go about determining that? Well, if there's an auxiliary hypothesis that you've got a good reason to think might be false, then you ought to look into it. So in the case of the Ptolemaic hypothesis, a lot of the proponents of Ptolemy's system said, hey, the telescope uses curved lenses. Curved lenses often distort things. Think about like a funhouse mirror. Why should we trust this auxiliary hypothesis that says the telescope gives us reliable information? So there, someone had a reason why it might be plausible that the auxiliary hypothesis was mistaken. If you've got a good reason to think an auxiliary hypothesis is mistaken, then you ought to test that. But what you don't want to do is simply ad hoc reject one of your auxiliary hypotheses because you want to keep around your hypothesis. Alright, we've got one video left in Chapter 7.